Welcome back to ECE 207. I think everyone is watching these videos from what I can see on the traffic on the website. Actually, they're a little bit delayed in terms of when they are posted, but they are on the D2L website. If you missed something, maybe you can go back to that particular time. So if you're watching or taking notes, maybe you can say, oh, at 30 minutes I didn't quite follow that. You can actually go back. You might as well get some advantage out of me doing this in terms of recording these lectures. This is the super lecture. I know all lectures are super, but the reason is that there are a lot of different supers in this lecture. We're going to talk about supernodes, supermeshes, and even what in the world? Superposition. There's all of our supers. We'll start by a review of what we've already learned from last time, which is going through nodal analysis, a quick example illustrating that, which hopefully will get you thinking about what we are trying to do with nodal analysis so that we can throw a wrinkle in the mix, which is look at supernodes. And then we'll start doing the same kind of explanation with mesh analysis. We'll start with mesh analysis, go through some examples illustrating that. In that, we're worrying about writing KVL equations. With nodal analysis, we're worrying about using KCL to worry about writing currents in terms of voltages. With mesh analysis, we're writing KVL equations really to find currents. And our meshes will look like picture or window panes. That's where the mesh, each of those will be a mesh. That's the idea. Obviously, this list of topics is rather long, and we need to get to Wheatstone Bridge before your homework is due. That's not going to probably happen today. Your homework is not due until a week from today. Homework number 2. Let's get started. And another one of those, analyze this. Analyze the following circuit. Using nodal analysis. And this circuit is a little different than the one that we finished with last time. But I'm hoping that if you go back, you'll be able to redo the class participation assignment that we had last time. We have a current source and 4 resistors. We'll label those resistors R sub 1, R sub 2, R sub 3, and R sub 4. And that is an independent current source we will call I sub S. If I'm wanting to analyze this, especially if I now tell you to do it via nodal analysis, what are we trying to identify, or what's maybe one of the first steps in the process of performing nodal analysis? Pardon?
Finding voltage.
Okay, we need to find voltages, and before we even do that, what do we have to find? The nodes, correct? We need to somehow determine what it is that we're going to call, or how we're going to reference these voltages that we want to define. Where's my reference node, or where would you suggest we put the reference node? Not that I'll live with what you suggest, but go ahead and try. How many nodes do we have? I heard 3 and I heard 4, and you're both right to an extent. Here's 1. There's 1. Actually, this is 1. Here's 1. And there's 1. There's 4 nodes, but I said 3 was right also. How could that be? You could actually combine R sub 1 and R sub 2 into one equivalent resistor and minimize your effort if we do it, and we're going to go ahead and do it this way, keep the nodes isolated, but this will give us 3 unknown node voltages, a V sub 1, a V sub 2, and a V sub 3. I'm going to call this my reference node, meaning I'm going to refer all of the node voltages to that location or that node. That will be my negative terminal on my node voltages. Let me then say that I will call this voltage from the reference up to that point as V sub 1. I'll go ahead and label that node 1. If I call that node 2, then I'm going to say that this is plus V sub 2 minus across the bottom resistor, R sub 2, or the horizontal resistor, and I will label this node voltage V sub 3. And I hope that you are understanding what I said before, is that we could, and when you're doing this, probably in practice, this is going to give us 3 equations and 3 unknowns. You now have to invert a 3 by 3 matrix. You may not want to do that unless you have your calculator with you or a computer. And if you were doing this by hand, I might just go ahead and combine those into R sub 1 hat. Not a bar, not a tilde, a hat. Today we're wearing hats. It may rain after class. So we have to put on a hat. And then I would just have 2 node voltages, V sub 1 and V sub 3, as I've defined these. And if I needed to find V sub 2, I could subsequently to finding V sub 1, because I could find the current going, well, we sort of know the current. Let's just find the KCL equations. Question?
I don't understand the way you denoted these. Why did you place at 2 different areas?
Okay, so V sub 1, I think the question is, I'm not quite clear what you're defining to be V sub 1 or why you defined it the way you did. Is that correct? Or is that the right interpretation of your question?
Yes.
V sub 1, maybe what you were thinking was this was V sub 1. Since it's supposed to be across R sub 1, it doesn't have to be across R sub 1. It's actually across those 2 resistors. This is not the same voltage.
So V sub 1 contains V sub 2?
V sub 1 does indeed contain V sub 2.
Okay.
V sub 1 is I'm hooking up my voltmeter. If it's not making sense, just think that you have a voltmeter and you're connecting the 2 leads, your ground or your negative lead and your positive lead of your voltmeter. You're putting your negative lead on the reference node and you're moving your positive lead around to these different locations and measuring the potential or the voltage dropped across those different nodes or those locations. Let's now write the KCL equations for those particular nodes that we've now identified, and this is actually then node 3 as defined. If I now write KCL at 1, I'm looking to find, let's say, the sum of the currents, the algebraic sum of the currents out of that node is equal to 0. I sub s is out of that node, and the other current leaving that node is, in terms of my node voltages, what is it? It's the voltage dropped across that resistor divided by the resistance. It's Ohm's law. If I want that current flowing down through R sub 1, and I want that current to be going down, and to be the passive sign convention, I need that current to be flowing from plus to minus on my resistor. Question?
I'm confused. Are we working this example as if R1 and R2, like combining them, or keeping them separate?
Good question now that I made it difficult by identifying that R sub 1 hat. Forget the R sub 1 hat. It doesn't exist right now for the analysis. So I'm just assuming that R sub 1 hat I have not found. I want to just illustrate 3 different equations, 3 different KCL opportunities. But what I was suggesting by indicating R sub 1 hat is if you want to minimize your workload, I would combine R sub 1 and R sub 2 into one equivalent resistor and then just have 2 nodes to worry about. But we're not doing that. We're eliminating the black encased combination of R sub 1 and R sub 2. And if I needed to combine R1 and R2, how would I combine those? Are they in series or parallel? They're in series, they would just add. Pretty simple combination. Now I want the current there, going down through R sub 1. How do I define that current as a formula in terms of my node voltages and my resistors? V1 over R1. Is that true? Remember what V1 is. V1 is spread over more than just R1, isn't it? R1 is not connected from V1 to ground directly. It's V1 minus V2. Does everybody see that? It's not, this is not your standard picture for KCL, but it is V1 minus V2. If that's a positive value, that will give me a positive result. I'm now saying V1 minus V2 over R1 is the current going down from that node number 1. Those are the only 2 currents leaving that node. Those have to sum to 0. There's one equation. We've identified 3 nodes. We should identify 3 different equations that contain V1, V2, and V3. We'll solve those for V1, V2, and V3, and we'll be done, essentially, with our analysis. In order to solve that for V1, V2, and V3, somebody would have to give us R1, R2, and R3 and the value for I sub S. That's a source. That's a stated current. Let's write KCL at 2. Really, I'm doing this example so that we get comfortable with writing these current equations or KCL equations. If we say the currents leaving node 2 equals 0, their sum, now I'm no longer really worried about that current. I'm worried about the current going there and that current. The current going up is, question? Okay. Okay, I think here, I'm sorry to interrupt, but I'm trying to understand where the question is coming from, maybe. There's a question with why do I seem to label my voltages in the manner that I did, my node voltages, and V3 seems obvious. Don't confuse the polarity of my node voltages with the direction of the current source. Those are disconnected. Don't worry about connecting or making the right call. You're not really deciding whether V1 is positive or negative. You're just labeling it. It's simply a label. It doesn't matter if it's negative, it will turn out to be negative. V sub 3 would be negative, let's say, if it actually ended up being negative. Right now what we're doing is with the reference node, we're using that to be our negative sign on all of our node voltages. And then we go to each of the other nodes, and that becomes our positive sign. Put your blinders on or cover up all the sources, the current sources. Don't worry about how that's going. That we don't worry about how that's connected or related to the polarity labels we're assigning to our node voltages. Does that make or help? Question?
Why do we draw the current down R1 the first time at 1, but then we're at 2, we draw it up?
Okay, why am I changing the direction of my current going through R sub 1? It's because I'm just trying to write governing equations. And I really am not trying to decide which way is the current going. I'm just saying for the equations that I want to write, I want to consider the currents flowing out of node 2. Currents going out of node 2, one has to go up, one has to go right. In the earlier situation where I was saying I want the currents leaving node 1, then I'm considering a current going down that vertical branch containing R sub 1 and a current going to the right. All I have to do now that I know that I want a current going up and a current going right out of node 2, I just need to define those in terms of my V1, V2, and V3. Now, you should find that this current going up will actually be the negative of what we just determined coming down. It seems to be that should be the case, correct? They're the opposite currents in terms of how we've labeled those. And if you're having trouble with that, you could just say, well, let me just negate the current that I just found, V1 minus V2 over R1, and now the current going up should be the negative of that, which is V2 minus V1 over R1. And indeed it is, using our analysis tools that we've been learning now. Start at the node we're at and subtract the one we're going to. That's the difference, positively from that node. If we use that logic, the current going up through R sub 1, how do I define it in terms of my node voltages? That's my vertical current going up. Is that making sense? And that should be the negative. If I was on stilts or if I had more spring in my legs, I would point to that last line, the one up above it. I'll cheat. Never mind. Glad this doesn't have video. Any questions on that current? Yes? V2 minus V1. What I'm wanting to do is I want the positive voltage dropped across R1 to be going from bottom to top, in this case, to give me a current going up. If V2 is larger than V1, that's going to happen, V2 minus V1. So just plug in some arbitrary numbers just to make it clear in your own head. Say V2 is 10, V1 is 5. 10 minus 5, well, maybe those are bad numbers because their difference equals one of the numbers. So V2 is 10, V1 is 3. Their difference is 7, but it's positive. 7 divided by R sub 1 will give me something going up. That would give me a current going up. Does that help?
Yeah. Is this the arbitrary? Could you just do V2 plus V1 since it's a current going through both, or the voltage across both?
The question was, can we just say V2 plus V1 over R1? And the short answer is no. The reason is that's not the voltage dropped across R2 in the positive direction that we want it to be positive. If we added V2 and V1, that's going to give us kind of a mess, actually. We want just the voltage dropped across R sub 1, just that voltage. And if we had a voltmeter and we kept the negative end here and started pointing with the other, we're going to measure 10 volts, then I guess I was going to say V2 is 10, V1 is 3, hypothetically. Then their difference is what we have across R sub 1. Question?
For both node 1 and node 2, we're assuming that V2 is bigger than V1.
Just in this particular equation, that's just to get this equation right. In the earlier one, we considered V1 to be bigger than V2 to convince ourselves that that formula was correct. We're just trying to write accurate equations. So can you
assume that V1 was bigger than the second one and subtract V2 from it? Just like we did.
well, if you consider V1 to be bigger than V2, then you're going to end up with a current actually going down. And that's negative of how we've drawn it. We've now mentally sketched that arrow going up. We want to define our equation such that we get a current going up, which is V2 minus V1. What's the current flowing to the right through R sub 2? Questions on that second equation? There it's V2 minus the reference node. There isn't any more to go. So that's the drop across R sub 2 is just V sub 2 as we've defined it. And that's what's going to happen with respect to the currents going through R sub 3 and R sub 4. If we now write KCL at 3, what are the currents leaving that node? Is I sub s leaving? It's leaving if I labeled it this way, correct? Minus I sub s is leaving. That's one way of writing it. Or you could say all the ones leaving equal the ones coming in. And then the ones coming in will be on one side of the equation, all the ones leaving are on the other side. It doesn't matter. That's why we've been doing algebra all these years. And somebody says algebra error and takes off all the credit, right? So make sure you do your algebra correctly. Maybe I'll give you 1 point for just me. The exam is 2 weeks from today, as a reminder. We have a current going through R sub 3. We want it to go down to be positive. That's V sub 3 over R sub 3 plus V sub 3 over R sub 4. That's the current going down through R sub 4. That's equal to 0. There's our 3 equations and 3 unknowns. So now the question was, could we have done V sub 3 over it? So what you were asking, I think, is can I combine R sub 3 and R sub 4 as a parallel combination of resistors and then do my current through those? And that's fine. It just, to me, it makes it more steps because I'm now doing a separate step to try to combine R3 and R4 unless they're easy resistors to combine. If they were both the same, the resistance combined will be half, and that maybe will be easy to determine. But this way I just keep them isolated or independent of each other and I can see where they're coming from. But that would have been okay. It should give you an equivalent answer. We could then write this in the standard form. And the reason why we might want to write it in the standard form is so that it's easier for me to be checking your work. But in this case, we have what's multiplying V1, what's multiplying V2, what's multiplying V sub 3, and all the other terms on the other side. Just performing algebra if we're moving things across the equality sign. Adding a minus I sub s to both sides. Adding 0. You can always add 0 or multiply by 1. That's how we do our algebra, and that takes us a long way. The second equation is I now have a minus 1 over R sub 1 V1 plus a 1 over R sub 1 plus a 1 over R sub 2 V sub 2 plus a 0 V sub 3 equaling 0. And finally, our last equation is 0 V1 plus 0 V2 plus 1 over R sub 3 plus 1 over R sub 4 V sub 3 is equal to I sub s. Questions on that? Let's throw a wrinkle into this process. Because I know you were just starting to feel comfortable, and we can't get too comfortable or you'll fall asleep, right? Wrinkle. Here's the wrinkle. The node voltage, or the NVA, now you can text that to all your friends. I'm doing NVA problems. They'll know exactly what you're talking about. The NVA process is made a little more interesting when we have voltage sources in our circuit, or when voltage sources are present. Whether those voltage sources are independent sources or dependent sources. And I think you have a dependent source in one of your homework problems. Let's look at an example. It's easier to do this with a specific example. And here's where we start getting into the super part of the lecture. This is going to involve what will be called a supernode. Our circuit is a current source on the left going up, a resistor, an independent voltage source, another resistor, where are my nodes? Or how many nodes do I have? Or where is my reference node? Don't everyone answer at once. And don't answer all questions at the same time. I've asked several questions, haven't I? There's our reference node. That one is the most common, or it contains most of the wire, more of the wires. Here's a node. Let's say relative to the reference, that's node 1, since it's involving R1. Here's node 2. And there's node 3, but if we're trying to define node voltages that are yet to be determined, what do we know about the voltage at node 3? That's given, isn't it? That's already told to us. That's V sub C. That's given. We don't have to solve for that, so let's not even worry about the voltage at node 3. We can sort of forget that one. That can be on the side of the paper. If we found 3 node voltages, or define 3 node voltages, really we just need to find 2 of those that are unknown, V sub 1 and V sub 2. And we can say here's V1, and here is V sub 2. Plus to minus, plus away from the reference node, and minus on the reference node. If I'm writing KCL equations, I might be interested in that current. I might be interested in this current. I might be interested in this one. And let's say this one. thinking ahead mentally, what's going to happen when I try to write an equation for the current I sub 4 at node 1? What's going to happen? I'm going to say, okay, V sub 1 minus V sub 2 divided by what? That's a voltage source. It could be independent, it could be dependent. In this case, it's independent. I have no idea what that resistance is of that source. I really don't know what I sub 4 is. I can't find an equation for it because there is no resistance that's identifiable from that source. That's the wrinkle. I sub 4, which is the current through the voltage source, is unknown. That's going to present a dilemma. Oh, come on. I'm trying to come up with ways that maybe I don't have to scroll. That might be what's causing me problems, but if that's as good as my equation or picture comes out being, I'm making matters worse. Oh. I didn't get all my nodes anyway. Oh well. Or all my information. Let me now go back and say how I'm going to remedy that problem. I don't know what the resistance is of that current source, and because of that, I'm going to just enclose it into a bigger node. I'm going to create a node that will encompass that entire source. And what do I know about a node in terms of the currents? If I have just a smaller node, what do I know happens? Does charge accumulate at that node? No. By KCL, the sum of the currents have to be algebraically equal to 0. So now if I just enclose a lot of my circuit into one thing that I'll just say there's a big supernode, coming out of that supernode algebraically all my currents have to sum to 0, right? Because I can't accumulate current even in that supernode. That's what I'm going to do with that voltage source. I'm going to just enclose it and forget it. It's like one of those infomercials. Set it and forget it. We're going to close it in and forget it for a little bit. We won't forget it completely. But we're going to create a supernode that contains the voltage source. And let me just refer you to page 74 of your textbook if you want to go back and read that. I was going to say Saturday night, but maybe you'll be doing something else Saturday night. But if you have nothing else to do, you can start working these problems. Should be starting before Saturday night. Here's the supernode that I'm creating. There's my supernode. If I want to now write the KCL relative to that supernode, how many, do you see the currents that I have to account for? Now mentally, I'm not even seeing that source. But I do need to go in there, and if I have polarity markings on V1, V2, V3, I have to use those particular voltages. I have my current source on the left coming in. Then I have everything else leaving, as to how I've labeled it. I have I1 going down, I2 going down, and I3 going to the right. Those are the four currents going in and out of that supernode. Does everybody see that? Let me now write the KCL at that supernode. I had I sub A coming in. That's equaling then everything going out. The first vertical current going down, bless you, was V sub 1 minus R sub 1. The next current going down, in terms of my node voltages that I had defined, is V sub 2 over R sub 2. What's my current going to the right? I sub 3. Needs to go to the right. It's what? I start where I'm at, or I write down the voltage that I'm at, which is node 2, V sub 2 minus V sub 3, which is actually a known quantity, V sub C, divided by R sub 3. Questions on that? That's the current going out of the supernode to the right.
How did you know that it was V2 minus V3 or VC?
I want to find I sub 3, and I've labeled it to be positive going to the right. If I want the polarities to be correct in terms of obeying the passive sign convention and Ohm's law, then the voltage dropped across R sub 3 positive from left to right is going to be V sub 2 minus V sub C. If it ends up that I sub 3 is actually going to the left, the signs will take care of themselves. But to be consistent with how I've drawn it, I need I sub 3 in my equations to be consistently positive, meaning I sub 3 needs to equal V2 minus V sub C divided by R sub 3. Question? Oh, so I think it's more of a statement in the form of a question, I think. KCL says the algebraic sum of the currents in or out of a node is equal to 0. Or you could just restate it. You could say the currents in equal the currents out. And usually I draw them going out just so that my process, I don't even hardly have to think how I'm writing the equations. It's just going to be, oh, if I want a current going to the right from node 2, it's the node that I'm at, V2, minus the node I'm going towards that is across R sub 3. So I now have V sub 2 minus V sub C. That's going to actually equal the voltage dropped from left to right across R sub 3. If it ends up being negative, it ends up being negative. That's okay. Doesn't really matter, but my formulas will be correct and they will anticipate that or account for that. Other questions? Did that?
Can you just say that last part one more time? Because I think that's
Did anyone get that on tape? I can't remember what I said. Can you rewind and play it back? I think what I said, and this may be a paraphrase. I'm saying I want my current I sub 3 to go to the right. And in order for that to be a positive current the way I've drawn it, I need to take V sub 2, where I'm at. Well, yeah. Yeah, you don't care what it ends up being, but in order to be consistent with the way you've sketched it, or actually the way I've sketched it, is I need V2 minus V sub C. That will give me the voltage from left to right across R sub 3. Whether that's positive or negative, that will come out in the wash.
Question, Professor.
Yes?
If you were to point I3 into the supernode, would it be V sub C minus V?
So now the question was, if I had actually relabeled I sub 3 and made it go from right to left,
Yes.
then what would my formula be? Well, then I would have to say I sub A plus this I sub 3 hat, those are both coming in, equal I1 plus I2. Is that clear?
Yes.
Then I would define I sub 3 to be V sub C minus V sub 2 divided by R sub 3, which should be just the negative of what I calculated for the I sub 3 that's actually drawn there. Is that clear? And if it's not, hopefully it will be clear before the exam, which is in 2 weeks. How many equations have I written so far? One. How many do I need to write? 2, because I have 2 unknown node voltages. Question? So where's the node voltage for the supernode? Well, my node voltages I've defined. Now what I have to do is figure out how, I never assigned a value for that. Is that what you're asking?
Yeah.
It's, who knows what it is. Let me look at my notes. What did I define it to be? That's a given. Somebody's giving you a battery and putting it right there, and let's just call it V sub B. That's my battery voltage. So that would have to be given to you. And now what you need to do, you've told me I've just written one equation. By making this supernode, I've actually eliminated, in this case, one equation. Normally you would write a KCL at node 1, a KCL at node 2. There were my 2 equations. Now I've combined those into one supernode, and now I just have one equation. It involves V1 and V2, but somehow I need another equation. Well, now you have to go back to your supernode and say, I need to relate what's inside there to my node voltages. Do you see a strategy for doing that? Can you define or find an equation that involves V sub B, V1, V2, and maybe the other parameter values? We've been using KCLs. Now we have to change and do a KVL. If you look at starting at the lower left or right at the bottom of R sub 1 and I start going up, I can now write a KVL equation around that little mesh. Minus V1, minus VB, plus V sub 2, those should equal 0. Does everybody see that? That's my second independent equation.
Can you explain that again?
I can try. I'm trying to come up with a second equation. I've already collapsed my 2 equations down to 1 with that supernode in terms of my KCL formulas. I want to find an equation that involves V sub B, which is my voltage source inside my supernode. If I look at that circuit, yes, I can actually relate V sub B to my node voltages. If I look at that and study at my middle mesh, if I walk around and do a KVL in that middle sub-circuit, I can actually find an equation that involves V1, V2, and V sub B. And that's just writing a KVL equation. Minus V1, minus VB, plus V2. And I'm living with how I define the polarities on my node voltages. I'm not changing anything after I start writing equations. I'm not changing the polarity on my voltages, node voltages. Here's what we're doing. I needed a second equation. Because I collapse things down by that supernode. What I'm going to do, or what I just said I would do, is I'm going to now write, using KVL, or write a KVL equation that involves the source inside the supernode. I've already verbally said this. The KVL with the supernode was I went up vertically, but I entered the minus terminal on V1 first, and that's what I write down. That was minus V1. Then I'm going from memory. Going from left to right, my V sub B was negative to positive. I enter the negative terminal first on that. That's now minus V sub B. And then I come vertically down to complete my KVL loop, and that I entered V sub 2 from the positive terminal. Those have to sum to 0. That's my second equation. If I now write those in standard form, my two equations, then I will be able to write or find two equations and two unknowns and do my linear algebra to find V sub 1 and V sub 2 once somebody tells me what my sources are and my resistors are. Question?
So even though V sub B is completely encompassed by the mesh, you use it in KVL?
So even though, the question was, even though V sub B is completely enclosed in this supernode, you can still use it in your equation. And the answer is yes, because this supernode is just something that's convenient for us to help us solve this circuit. We had no way really of continuing with our standard technique of trying to say, what's my current going through that voltage source? I don't know. So we eliminated that problem by making a bigger node, a supernode. But that voltage source did not go away. It's still in our circuit. And we can actually relate that to these node voltages that we've defined. And one way to do that, or the way to do it in this problem, is to go ahead and use KVL around that inner loop in our 3-mesh circuit. And that allows us then to rewrite or identify one more equation that involves V sub B and the two node voltages, V1 and V2. Is everybody okay with the correctness of that equation? That's KVL. And you haven't done anything wrong. You've just written a KVL equation in terms of your two unknowns and your given independent voltage source, V sub B. And you have obeyed the polarity signs that were assigned or that you created. If I now, does that help answer? Here's the standard form. We had the one equation, 1 over r sub 1, the first equation, times V1 plus 1 over r sub 1 plus 1 over r sub 2, V sub 2, equaling I sub A plus V sub C over r sub 3. Remember, V sub C was a source, and that's to be given. And a voltage divided by a resistor is going to give us a current. So our units are compatible on the right-hand side. We can add those up. If I sub A was 2 and V sub C over R sub 3 ended up being 6, then the right-hand side is 8. Nothing magic about that. Question? Oh. I'm falling asleep up here. Does that look better? Let me go back to my circuit. I don't know what I was doing. I was sleeping. Doing it with my eyes open and my mouth running, that can be dangerous. Does that look better? So I need to just turn it. Thank you for that correction. I'm just seeing if you're awake. Sure. Questions? Any more questions on the validity of that equation? Is that now accurate? Then we have the final one, which is minus V1 plus V sub 2 equal V sub B. There's our two equations in the two unknowns, V1 and V2. And we can solve those using linear algebra. Questions on that example, or how you might use the Supernode?
On an exam, are we gonna have calculators?
I haven't even, the question is on the exam, are we going to have calculators? I haven't even thought that far ahead. I'll try to post a practice exam and I'll look at that and see, yes, you'll probably be allowed calculators.
Okay.
So if you have a favorite way of solving simultaneous equations, you may want to get practiced at it, if that's what it involves. I may just have you, since I'm doing all these standard forms, I may just say put it in standard form. And it may not involve any numerical values for some problems. Because I'm assuming, given enough time, you can find V1 and V2. I want to know, can you actually work the problem to get it in the stage that you can just turn the crank? That's more important to me. That said, I'll probably give you a 10 by 10 with numerical values and say, give me the, no, tease. Other questions? There's nodal analysis. Let's now talk about the next analysis technique, which is mesh or loop analysis. I had no constraints on node voltage analysis. With mesh analysis, I actually have a constraint. This doesn't work for all circuits. This works for planar networks. So if you're given two pictures, which one is planar? I'm sorry. That's planar than this one. What's planar mean? We'll try to make that clear. What does it mean by planar? A planar network can be drawn this will really make you on a plane. So you need to get on a plane and draw this network. No, not the flying plane. This is a surface plane, a plane surface with no crossing branches. And crossing branches is what you have to pay particular attention to. For example, suppose that I have the following circuit. Is that circuit planar or non-planar? Can I draw that circuit with non-crossing branches? The key phrase or word is can I. This one obviously is not drawn with non-crossing. It looks like there's something crossing, but there's no physical connection with that hump in the middle. That means that that particular connection from here to there it's not electrically connected to the connection from C to D. Does that make sense? Meaning, I can actually stretch that resistor between A and B and pull it outside and actually draw the circuit differently so that it is a planar circuit. This one is a planar circuit because this is equivalent to the following. It's this, except now that one that I had going from A to B, I now just lifted it up and stretched the wires. That's now equivalent, and so that one is planar. I have all of my circuits or elements on a plane surface and none of those are crossing. And because of that, I can actually say that I can start, in a sense, going around each of these little pieces in what we will call meshes or loops. What's an example of a non-planar circuit? And I'm going to make it really crazy. Whoa. Can I pull those apart and in the trick that I did before and get them all to where something eventually doesn't cross? No.
It's so hard to tell.
It's so hard to tell. Well, you guys are non-electricals. You're more visual. You can draw me better than I can. But if you try to pull those apart, you're going to see that you're always going to have something crossing. Meaning, these circuits you will not be able to write mesh equations for. You can't go around a mesh without crossing over. So this is a non-planar network. Needless to say, we won't have something quite like this on your exam unless, what? You could apply node voltage analysis to this. You just couldn't. What was the laugh for?
You could do it, it's just you really couldn't because of practical purposes.
Oh, don't cut yourself short here on this. This is a Saturday night problem right here. This is how you relax. Question. Pardon? The previous drawing. Now, I can't do that. You're going to find a problem, probably. How far back? That one we could actually bend the wires around or lengthen those to make it such that we had all of these isolated little meshes or windows or window panes. The other one, the non-planar one, that's not possible. We can't separate that out or pull that out to where you have all of these little isolated meshes. Now if we start going around one, we're actually going to trip over a wire. Here's our mesh analysis. Let me just tell you where it's located. The analysis process, mesh analysis process, is presented on page 83. This too has a wrinkle. So I'm just going to tell you that before we get into all of this. Let me just say that there is a wrinkle, and if you relate it to what we talked about before, what do you think gives rise to the wrinkles in this one? When we were writing node voltage equations, whenever we had voltage sources in our circuit between node voltages, that gave us a problem. Here, what kind of sources do you think will give us a problem? Current. If we have current sources present in the wrong spot, that could present a problem. Let's just work an example. If we have a current source in the right place, it actually might make our job easier. But we'll learn that as we go. Here's a circuit. V sub A, I'll do that first before I forget it. Then a resistor R sub 1, a resistor R sub 3, a resistor R sub 2, R sub 6, R sub 5, R sub 4, and here's V sub B. If you had to identify nodes, how many nodes would you have? 6. So that would be a 6 by 6 matrix that you would have to invert to find those, well, I'm sorry, 6 nodes. One of those you would pick as a reference. You would have 5 node voltages. Now what we want to do is write this in terms of currents, mesh currents in particular, and we'll define those obviously enough to be contained within these little meshes or windows. Let's say this is I sub 1. Let's say this mesh involves a mesh current. These are mesh currents that I'm writing. That's I sub 2. And here is I sub 3. To make things nice and consistent, it's best to just keep those moving in the same direction. All of my mesh currents are all going clockwise. You can define them however you want, but to make them nice or neater, it's probably best to just establish a direction and stick with that. There are my meshes. So I've identified my meshes. Those were the 3 window panes, if you view that as like a window. And once I define those 3 meshes, I can now define my mesh currents. Now I'm just going to have 3 equations in 3 unknowns instead of 5 equations in 5 unknowns. So in this case, it might be more economical manipulation-wise to write mesh equations than node voltage equations. That's why we're studying another technique, because you're probably saying, well, if this has limitations or restrictions, why are we even talking about it? Node voltage seemed to work for everything, and it does. But in some cases, it may be more straightforward to do one analysis technique versus the other. Does that make sense? In this case, mesh analysis seems to bias something over node voltage analysis. Now we're just having to find 3 equations instead of 5. We now want to write KVL around each mesh. And once we're finished with that, we will go ahead and rewrite in standard form. I probably shouldn't do this before we even get started, but let me just put together an observation. If somebody said, you know what, I would like to know that voltage, V sub 2, and if somebody gave me this current, let's call it I sub D, you could determine V sub 2 from Ohm's law, right? So this is the observation. What we want to do is understand how we're actually going to write V sub 2, and we're going to just do it without explicitly defining things like I'm doing now. But this observation is designed to help you think through that process, which hopefully you won't even hardly have to think once we start doing it. In terms of V sub 2, though, V sub 2 is R sub 2 times I sub D. Everybody sees that by Ohm's law, correct? I'm going to be writing all of my equations in terms of not these individual little currents, but in terms of these general mesh currents, I1, I2, and I3, which is not I sub D. But I can relate I sub D to I sub 1 and I sub 2. I can do that several different ways. Maybe the easiest for now is to say I'm going to identify that node, and I know because charge cannot accumulate at a node, I can write KCL at that node. I'm talking my way through this before I advance the screen because I think advancing and going back and forth on the screen is what's causing the problems. So let me talk my way through it and then I'll write down the equation. I'm trying to relate I sub D to I sub 1 and I sub 2. The other way that you can think about it, we'll write KCL at node B, but another way of thinking about it is I want I sub D to be going positive in the direction that I've indicated, which is vertically down. That's the red I sub D. If I try to think of that in terms of I1 and I2, hopefully you see the algebra staring at you. If I sub D is going down, then I sub 1 is going down, I sub 2 is actually going up, meaning I sub D algebraically is just I1 minus I2. That's really, you're just mentally doing KCL at node B. Let's do that. Here's the observation that I'm trying to make before we even get into all of the equations. The observation is V sub 2 is R sub 2 times I sub D. But now you're saying, what is I sub D? We want to write V sub 2 not in terms of I sub D, but in terms of I1 and I2. That's going to be our strategy. We want to write all of these voltage drops in terms of these mesh currents. For this case, we can convince ourselves, hopefully, if it wasn't clear before, if we do a KCL at B, I had I sub d going down into B. Is that true? Now I can't even remember. Falling asleep. Is I sub 2 going in or coming out? Oh boy, this is a tough one. Out and in, isn't it? So now let's look at that. I'm maybe making it worse. Here's node B. Here was I sub D. Here was I1, and here was I2. Is that correct? Now, what I really want to be thinking about is this current coming in there, and maybe this current going out there. If I knew this current, I sub x, and if I knew this current, I sub y, you can write KCL, right? You now know that I sub d, that's going in, plus I sub x is equal to I sub y. That's KCL. What I now need to convince you of is that I sub x, the only current flowing in that path is which current? What's the only current flowing through or defining I sub x? I sub 2. What is the only current making up I sub y? I sub 1. Meaning my KCL at B is actually I sub d plus I sub x, which is indeed I sub 2, and that's equal to I sub 1. That means that I sub d is actually I sub 1 minus I sub 2. That's what we were trying to show. That's the one that when we were just picturing it in our head or looking at it, we said, oh, ID is coming down, then to be consistent with that, I1 is going in the direction of I sub d, so that's positive. I2 is going away from I sub d, that's negative. It's I1 minus I2. That's what we just derived. In terms of now I1 and I2, what is this voltage drop from top to bottom across R sub 2? That's V sub 2 as we defined it. Here was our R sub 2, here was V sub 2, and here was I sub d. But we just said that this was I1 minus I2 as we had defined it relative to I1 and I2. Questions so far?
Why if you go back up?
No, I'm not going back up, but ask your question and I'll try to remember.
Since the I2 goes around, so I mean it goes up out of the node and then back into it.
Yes, so the question, how did we pull out and say that I sub x was actually just I sub 2? It's an interesting question, a valid question. I'm just going to try to have to convince you of that. Going in the vertical R sub 2, there's several different currents that we've associated. There's a I1 is going through there, I2 is going through there, and I sub d is going through there, as we've defined all of those currents. The only current, though, going through R sub 5 is I sub 2, as we've defined it. The only current going through R sub 3, as we've defined it, is I sub 1. And I sub 1, then, going through R sub 3 is whatever we called it, I sub y. And I sub 2, which is going through R sub 5, from right to left, is I sub x. That's how we define those. The point I'm trying to make, which I'll go ahead and release you after I make this comment, is that I sub d is made up of I sub 1 and I sub 2. You just need to figure out how it's made up of those and get the sign correct. The easiest way, I think, is to visualize and say I sub d is being helped by I sub 1, so that must be positive. It's being hurt by I sub 2, that's negative. So I sub d is I1 minus I2. We'll pick up at that point on Thursday.